Hey everybody, today we're going to start chapter 5 with an introduction to probability. It is definitely a challenging chapter, so make sure that you are focused and that if questions ever come up, please ask them as soon as they come up. So we're going to start this chapter off in the way that we always do with some sort of an activity. So this one is called 1 in 6 wins. So a soda company printed a message inside the bottle cap lid with "Please try again" or "You're a winner." They advertised that 1 in 6 wins a prize. 7 friends each buy 1 soda at a local convenience store, and the clerk is surprised when 3 win a prize. Are the friends lucky, or is the 1 in 6 claim inaccurate? Now, we're going to be talking a little bit later on today about simulations and how it is that we can simulate chance events. So that's what we're going to do. We're going to simulate this chance events by using a model, and the model that we're going to use today is a 6-sided die. So 1 through 5, if you roll a 1 through 5, that means "please try again," and 6 means "you're a winner." Now, because I'm assuming you don't have 7 die at home, we're going to go to random.org and use their dice simulator, and they have the ability to roll 7 dice at once. So that's what we're going to do. So we're going to roll the dice 7 times to imitate the process of the 7 friends buying their soda and count how many won a prize. Then we're going to repeat this for 9 additional trials, so we have a total of 10 trials. Then you're going to go to the collaboration space, and under semester 1 activities in the collaboration space, there's a page called 1 in 6 wins, and there you're going to record on the dot plot the number of friends that won for each trial. So you yourself are going to be entering 10 dots on the dot plot in the collaboration space under semester 1 activities. So then once we look at the class data, we're going to decide together, does it seem plausible that the company is telling the truth or that the 7 just got lucky? So I wanted to make sure that I showed you how to do this. So I told you I went to random.org, but then I went to games and then I did dice roller. And then when you go there, it says, how many would you like to roll? And I'm going to say that I would like to roll 7 virtual dice. So I'm going to roll the dice. And each one of these is going to represent my 7 friends. Now remember, 6 is the winner and nothing else wins. So of these 7 friends, 2 were winners. So the first dot that I would put on my dot plot would be the number 2. 2 of my 7 friends won. Then I would roll it again. And I would find that 1 of the friends won. Then I would roll it again. And now this time 0 of the friends won. So that would be 3 different trials. You're going to do a total of 10 trials that you're going to put on the dot plot in the collaboration space under semester 1 activities. So really, what is probability? Probability is the mathematics of chance. Statisticians use random samples and random experiments to avoid bias. So probability and looking at random chance events and the mathematics of chance is super important to statistics. So the basis for probability and the basic idea behind probability is that chance behavior is unpredictable in the short run, but very predictable in the long run. Now we're going to talk about this by looking at a simulation with coin flips. So if you think about it, the long run probability of flipping a coin, 50% of the time it's going to be heads, and the other 50% of the time it's tails. So let me show you that in a simulation. Okay, everyone, so this is the simulator, and here's your chance to guess. Is it going to be heads or is it going to be tails? We're going to flip a coin, and the coin is going to pop up here so you can see what it is. And then the simulator is always going to count the number of heads and proportion of heads. So here we go. Tails. Okay, let's toss it again. Ooh, another tails. A third tails. Wow, I would not have predicted that. But again, these are chance events. 4 tails, 5 tails, 6 tails, 7 tails, 8 tails. There's a head. Okay, so is it unlikely for that to occur? Absolutely. But can it happen? Yes, because in the short term, chance events are unpredictable. However, if I start making this be 10 tosses, and I start doing this, you're going to see that it's going to go towards the true proportion, which is 50%. So in the short term, yeah, there were a bunch of tails in the beginning, but if I were to repeat this chance event many, many times, I'm going to see that slowly over time, as I do this here, the probability is going to be closer and closer to 50%. So although I started off with a string of just tails, over time, I can pretty much say, yep, there was a 50% probability of getting heads or tails. So this idea in probability is really important, that in the short run, it's not predictable, but in the long run, it is. So I told you on the last slide that if you toss a fair coin, the probability of getting heads is 0.5. What does that mean? Well, the probability of an outcome of a chance process is a number between 0 and 1 that describes the proportion of times the outcome would occur in a very long series of repetitions. If the outcome never happens, the probability is a 0. If it happens every time, the probability is a 1. But most probabilities are somewhere between 0 and 1. So what about this idea that I said that probability is unpredictable in the short run, but predictable in the long run? The idea behind that is called the law of large numbers. That says that if we observe more and more trials of any random process, the proportion of times that a specific outcome occurs approaches its probability. So the more times we do something, the closer it will be to its true probability. Let's have a word about randomness. Let's say I want to pick 5 intersections in downtown Seattle area. Okay, when people generally say random, that aren't in statistics class, they think like spread out. So they might be like, oh, here's a random intersection, here's another one, here's a third, a fourth, and a fifth. That looks really random. But those aren't random at all. I was very intentional with the dots that I chose there. If I truly wanted to be random, all possible combinations would occur. So for instance, if I could randomly select out of a hat intersections that were all, let me erase these original ones, I could randomly select intersections that were all right here. And that could be random. Random is a chance, truly chance event. So now we've taken an example and we talked about randomness. So what we're going to do now is we're going to talk about simulations. And the 1 in 6 game that we just did was a simulation. To give you a little recap from yesterday, we talked about the simulation process and I kind of broke it down into 3 steps. So when you're simulating a chance event, the first thing you need to do is describe how to use a chance device to imitate one trial, aka we're going to call it like a repetition of the simulation. You're going to tell what you're going to record at the end of each trial. Number 2, you're going to perform many trials of the simulation. And then 3, you're going to use the results of the simulation to answer the question of interest. Now these sound a little bit vague, so I'm going to walk you through each of these steps with a specific example. And that example is the example we looked at yesterday. So the example we looked at yesterday we called airport security. And I'll go ahead and read it out loud. The Transportation Security Administration, TSA, is responsible for airport safety. On some flights, TSA officers randomly select passengers for an extra security check prior to boarding. One such flight had 76 passengers, 12 in first class and 64 in coach. Some passengers were surprised that none of the 10 passengers chosen for screening were seated in first class. We want to perform a simulation to estimate the probability that no first-class passengers would be chosen in a truly random selection. So basically, we're questioning the TSA and we want to know what is the likelihood of getting 0 first class out of 10 passengers. So now the question is, how do I do this? Right, so let's go back to step 1. Step 1, I need to set up my random chance device.
So I need to use the given proportions that were given to me to sort of set up my random chance device. For example, when we played the 1 in 6 game, we used a dice because we needed 1 to be the winner and 5's options to be the losers. So we decided that we would roll a die. 6 would be the winner, 1 through 5 would be the losers. That would represent the proportions given or likelihood probabilities of winning. Now, in this example with the TSA, we have first class passengers and we have coach passengers. There were 12 passengers that were first class and the rest of the 76 passengers were coach. So how could I do that? That's a lot of numbers. That's more than a dice. That's more than a coin flip. So a random digits table is going to be our best bet here. So the way I would set this one up is I would say 0, 1 to 12 are going to represent first class individuals, and 13 to 76 are going to represent individuals who are in coach. And then I'm going to ignore all other numbers. Okay, so step 1 is just set up my random chance device, right? And then the next step would really be to say how you are going to do this. And that involves number 2. So we're going to pick numbers from the table until you reach the number selected in the example, and this is considered one trial. So in the example that I just set forth, there were 10 people randomly selected from the TSA, and 0 of them were first class. So we had 10 people selected. So we want to take our random digits table and look, okay, I'm going to look for 10 numbers. When I find those 10 numbers, I'm going to see which of those numbers are going to represent first class. So this time there were 10 people selected at random, so I would pick 10 numbers looking at no repeats because once a person is selected, they can't be selected again from the TSA. Then I would repeat this with many trials. We did this with the 1 in 6 game. When we were using the 1 in 6 game, you had the likelihood that 3 people out of 7 could be winners. So you took a trial of 7 individuals and you saw how many times 3 or more of them won. That would be one trial. You then repeated that trial 4 more times for an addition of 5 repetitions. Hopefully that makes sense, the difference between a trial and a repetition. Okay. So now what we need to do is we need to use the results to draw a conclusion. So I would take, in the TSA example, I would take my 10 individuals, or the 10 numbers that I picked, and I would see how many times did I get 0. So total up the number of times that 0 first class people were chosen, and then I would count that out of the number of trials that I did. So let's say in trial number 1, I picked 10 numbers. One of them was a first class passenger. Then I do another trial. 2 of them were first class passengers. Then I do a third. 0 were third class passengers. Then I would say, well, 1 out of 3 of my trials had 0 first class passengers. So then I could use those results to draw a conclusion. I know this is complicated, so I want to give you some time to actually practice it with this example. So I'm going to have you and the woman next to you perform one trial of the simulation using the random digits table that you see before you. So you're going to copy the digits onto your paper and mark directly on or above them so that someone can kind of follow what you did. All right, and then once you've done that, then you're going to basically say, okay, well, in 15 of the 100 trials of the simulation, none of the 10 passengers chosen was seated in first class. Does this provide convincing evidence that the TSA officers did not carry out a truly random selection? Please explain your answer. So I'm going to give you a little time to do that, and I guess I'll just, I don't know, listen to some Kahoot Halloween music. Okay, if you still need some more time, which I think you might, go ahead and pause the video. Okay, so now that we're back, let's go over the answer to B. So for B, this is what I would have done. So looking at the numbers here, I have bolded the numbers that I would have chosen that are actually in our range. So 71, that's a coach passenger. Then I would look at 48, coach, 70, coach, 99, out of range, 84, out of range, 29, coach passenger, 07, ooh, first class, underlined. Just so we know this represents something different. 71 is a repetition, so I would ignore it. 48 is a repetition, so I would ignore it. Then we have 63, 61, 68, 34, all of which are coach passengers. Then we have a 70, which is out of range, and a 52, which is a coach passenger. And that brings us to our 10th and final number selected. So if I look at all of these bold numbers, only one of these bold numbers is a first class passenger. Okay, so let's go on to C. In 15 of the 100 trials of the simulation, none of the 10 passengers chosen was seated in first class. Does this result provide convincing evidence that TSA did not carry out a truly random selection? Explain your answer. Well, 15 out of 100, this should be some nice math, is only 15%. But 15% is larger than 5. So I would say, do I have convincing evidence that TSA officers did not carry out a truly random selection? No, I don't have convincing evidence. 15% of the time you will get results of 0 first class passengers being selected. So I have no reason to believe that they have not carried out a truly random selection.
So this is a homework problem for you to try. This is actually number 12, so we can do this together, although I am going to give you some time to think on your own for a bit. So Scrabble, in the game of Scrabble, each player begins by randomly selecting 7 tiles from a bag containing 100 tiles. There are 42 vowels, 56 consonants, and 2 blank tiles in the bag. Kate chooses her 7 tiles and is surprised to discover that all of them are vowels. We want to perform a simulation to determine the probability that a player will randomly select 7 vowels. So the first step is to describe how you would use a table of random digits to carry out this simulation. Then it says perform one trial of the simulation using the random digits given. Copy the digits onto your table. Let's just stop this. Okay, so this is number 12 on your homework. So we're going to kind of do this one together, although I am going to give you a chance to kind of pause the video and think about this. So this is about Scrabble. So Scrabble. In the game of Scrabble, each player begins by randomly selecting 7 tiles from a bag containing 100 tiles. There are 42 vowels, 56 consonants, and 2 blank tiles in the bag. Kate chooses her 7 tiles and is surprised to discover when all of them are vowels. We want to perform a simulation to determine the probability that a player will randomly select 7 vowels. So the first part says describe how you would use a table of random digits to carry out this simulation. So remember that when you're using a table of random digits for a simulation, the numbers, the range of the numbers, like 00 to 99, they have to represent the probability of each event occurring. Now we're told that there's 42 vowels, 56 consonants, and 2 blank tiles in the bag. That should give you a clue as to the numbers. So I'm going to go ahead and have you pause this and think about how you would describe how you would carry this out. Okay, if I were doing this, because I don't want to go into 3 digits, I'm going to make sure that I'm using 2 digits in each time. So I would say that I'm going to have 01 to 42 represent the vowels. I'm going to say that 43 to 99 are going to represent the consonants, and then 99 and 00, see what I did there, are going to represent the blank tiles. So then moving from left to right across a row, looking at 2 digits at a time, so pairs, I would read them until I have 7 unique numbers, making sure that I'm avoiding repetitions. So again, I chose 7 because Kate is choosing 7 tiles. So then I would record whether all 7 numbers are vowels or not. And then I would perform many trials, and then I would determine what percentage of the trials had all 7 numbers between 0, 1, and 42 representing the vowels. So going back to the 3 steps I told you in the simulation process, I described how I would use the chance device, like I set up what the numbers would represent. I mentioned that I would perform many trials, and then although I didn't actually do it, I said that I would use the results and answer the question and how I would do that. Okay, so let's go on to part B. Perform one trial of the simulation using the random digits given. Copy the digits onto your paper and mark directly on or above them so that someone can follow what you did. The great thing about this is all numbers are in use, so there aren't any that aren't in range. So I'm going to look over every 2 numbers, and I'm looking for my vowels. So 0, 0, 69, 40. Oh, 40. That's a vowel. 59, 77, 19. That's a vowel. 66. I think that's 7. 1, 2, 3, 4, 5, 6, 7. Okay, so I ended up with 2 vowels in my simulation out of 7. So part C is, in 2 of the 1,000 trials of the simulation, all 7 tiles were vowels. Does this result give convincing evidence that the bag of tiles was not well mixed? Why don't you go ahead and pause the video so that you can answer this yourself. You know this one. Okay, so as you knew, yeah, there is convincing evidence that it wasn't well mixed. If the bags, so you have about a 0.2% chance of getting 7 tiles that are all vowels. This is highly unlikely. So because this was unlikely to happen by chance, we have reason to believe that the bag was not mixed well. And that's it. Now it's time for you to try homework on your own. Have a great day.